So LC. There was another portion of the circuit that was used to charge up the capacitor. The energy in the capacitor was then set aside, and we connected that capacitor to an inductor and showed you through Kirchhoff's laws that there would be an oscillatory system. It generated a Kirchhoff's relationship of minus Q over E, where this was the original charge on the capacitor. I'm sorry, why did I put that there? Q over C minus L di dt. We showed that this could be written as a second order differential equation. So and then we talked about ways in which we could solve for a function that met the criteria that is pictured in this second order differential equation. And by the end, we had a couple of possibilities. And we had to pick which one of these was the more reasonable solution. And we threw out this one because we stated that this represented the charge on the capacitor, and the charge on the capacitor would be full at time equals 0. So we wanted to have a situation in which our trig function matched up with the expected charge relationship. So that gave us a time-varying function that looked like this, where omega was equal to 1 over the root of LC. All right? So I think that's about where we ended up on Friday. And then as the bell rang, I tried to throw out a couple of reminders from the prior year. First was that omega is known as angular frequency. Meaning omega had to be in radians per second. Because inside the parentheses has to be something that is in radians so that we can take the trig function of it. That suggested then that if we multiply this, if we divide this by 2 pi, we could get the oscillatory frequency. This would be converting from radians to oscillations. So the oscillatory frequency looks like this. Right? If omega is 1 over the root of LC, then the oscillatory frequency would be 1 over 2 pi times the root of LC. Yeah. Oscillations per second or hertz. So I'm bringing this up because we tend to think of frequency not in terms of radians per second, but in oscillations per second. So converting it to the oscillatory frequency makes the most sense. And yeah, we would expect this to be in hertz. The period of oscillation is just the inverse of the frequency. But generally, electronic circuits tend to oscillate fast. And one of the things that I wanted to remind you from last year, for those of you who had mechanics, is that we tend to use frequency for things that oscillate quickly and period for things that oscillate slowly. So it's way more likely to have electrical circuits that oscillate with very high frequencies. Now, that's kind of the end of our discussion on Friday. And I think that brings us to where I was trying to say, what's the point of this kind of circuit? Well, there are plenty of circuits where you want to have something that's happening in a regular and repeated way. this frequency, you'll notice, is dependent upon things that you could establish in your circuit. You can choose the capacitance and you can choose the inductance, so you can choose the frequency that your system oscillates. Now, can you think of anything that you're aware of that has an electrical circuit that oscillates? I got several people with their hands in the air. So let's start. Yes, sir. What's that? Sure. Speaker's going to have an LC system of some sort. Yes, sir.
A clock.
Clock of some sort. If you're going to have an electronic watch can tell time by using an LC circuit. You'll have to give me more information there. A drill is a motor, so it's going to just be circular. Its rotational rate would probably depend on the current in the coils of the motor, although it does oscillate technically, because things that are going in a circle oscillate. Now, certain kinds of chargers work. Key charging does work at a specific frequency, and so the inductor coils on a key charger. Do you guys know what I'm talking about? Anybody have a wireless charging mount or something? Well, if you tear this apart, you'll find inside of it is a coil of wires. That's the inductor. It's connected with a capacitor and a driving circuit so that it can generate a frequency of oscillation. It charges using electromagnetic frequency. The inductor coils act as the inductor inside that circuit. Emil?
The TV or monitor work?
Well, you're getting to pretty complicated things. So yeah, I am sure that there's required something that has a clock structure there. But let's anything that has the word hertz in it, that's electronic, at some point or another has to have something that is timing the system. So every single multiprocessor out there, which currently most multiprocessors are in the gigahertz range, somewhere in that circuit is something that causes the clock function of that processor. So if your phone has a gigahertz processor, something that is oscillating that many billions of times per second, there has to be a clocking function somewhere in the circuit that is dedicated to establishing the clock rate. Now, today's modern electronics can do this on semiconductors, but the old school way of clocking a computer was with a simple LC circuit built on your motherboard that established the clock rates for all the objects on your motherboard. Now, most modern computers don't clock that way, but the old days they did. All right, so let's get back to the stuff you want to know so it's on your homework. I'll try to make your homework extra hard. I had a couple of questions. Since some of you got that bored look on your face, I want you to derive the function for the current. You should know how to do it. I'll give you about 60 seconds to do so, and I'll call on the first person with the most bored face. Front row, I'm looking at you. Hurry. This one's easy. You can be a star today. So, you didn't have to do very much here. So I am a little disappointed. Current is just a derivative. So all I should see is minus. I should see an omega out here. I should see Q max out here. And I should see sine of omega t. That's it. That's all you had to do. So we'll stay on focus and tasks here so you guys can get more physics and less laughter. You should be able to calculate the energy of the circuit. The energy is transitioning from the capacitor to the inductor. And we know that at any point in time, the energy in the capacitor as a function of time would have to be equal to 1/2. Now I want this in terms of charge, so that's going to be Q over C squared. I'm purposely using the lowercase q because q is a function with respect to time. And we already talked about the fact that the energy in an inductor as a function of time would have to be 1/2 Li squared. This is wrong. It's q squared over c. Sorry. Now, we already know that the energy in the LC circuit began inside the capacitor. But once we connected the capacitor to the inductor, that energy is oscillating back and forth. When we have maximum charge in the capacitor, all the energy is on the capacitor. But when we reach the point where we have maximum current through the inductor, all the energy is in the inductor. You should be able to show that the energy in the system is constant by showing me that the sum of these two equals a constant. You should be able to show this. Everybody who had mechanics last year, we did this. But for you guys who don't remember, which is probably everybody, or have never done it before, do this. This is easy. Everything you need is sitting right in front of you. Everything on the screen is what you need for this. Make it happen. So I indulged all of your questions. You have to indulge mine. That's what I'm asking. I have Q as a function of T right here. And I have I as a function of T right here. That's what I'm asking you to do. Plug those in. See what happens. I see the disconnect. Let's connect those dots. See it okay? Just add it up. You might need to do some substitutions in here. There are some substitutions worth considering. Now, I need you to make progress here. So if you haven't made progress yet, perhaps take a look at your coefficients in front of each of your trig functions. I've got Q max squared over 2c all times cosine omega t squared. But on the other side, I've got L omega squared Q max squared over 2 times sine of omega t squared. Now, this doesn't look constant, but work on it. Omega is 1 over the root of LC, which means omega squared is just 1 over LC. Try plugging that in. I told you, everything you needed was on that page. So, Q max squared over 2c cosine omega t plus L Q max squared over 2LC times the sine squared of omega t. Do you see it now? All I did was plug in 1 over LC for omega squared, and I can cancel the L's out here. Now, don't pack up. I earned this time. Q max squared over 2C can be factored out, leaving you with cosine squared omega t plus sine squared omega t. And you're supposed to know that the sum of cosine squared and sine squared is equal to 1. So you get the total energy in the circuit equal to Q max squared over 2C, which is the amount of energy that was in the capacitor when we started. So it does sum to be equal to a constant. That's what you needed to be able to show today. All right.